Inside a corona treatment station, a ribbon of plastic film races past a bank of electrodes charged to thousands of volts. At the gap, the air ionizes into a faint violet glow. Something has to hold that charge in place without conducting it, without softening in the heat, without breaking down in the ozone. Metal would short it. A common plastic would char and age. What survives that zone is a hollow square ceramic tube, machined to drop straight into the electrode frame. 4 demands meet in this one part. It has to insulate. Standing between a high-voltage conductor and the grounded frame while the discharge runs without pause. It has to fit. A square or rectangular bore that seats the conductor and locks into the cassette exactly where the design expects it. It has to stay intact, resisting the chips and edge damage that cutting, handling, and assembly invite in a brittle material. And it has to endure, shrugging off the heat, ozone, and long running hours that would embrittle or distort a weaker material. The reason one fired tube can do all of that traces back to its crystal lattice. At full density, the material takes the form of corundum, alpha-alumina, where oxygen ions pack into a tight hexagonal array and aluminum ions lock into 2/3 of the spaces between them. The bonds across that grid are part ionic, part covalent, and they leave almost no free electrons to carry current. That structure gives a volume resistivity in the range of 10 to the 12th to 10 to the 14th ohm centimeters, and a dielectric strength on the order of 10 kilovolts per millimeter of wall. Lifting purity from 95 toward 99.7% alumina drives out glassy grain boundary phases and pores, steadying that insulation and raising strength. Fully oxidized, the surface stays chemically inert. It will not oxidize further, and it resists the ozone the discharge keeps generating. Geometry is where each order starts to diverge. The confirmed capability runs as a ladder. An 80 by 80 mm section reaches up to 500 mm long. 55 by 55 extends to a meter. 40 by 40 reaches 2.5 meters. And a slim 25 by 25 section can be drawn out to 3.5 meters. Real corona electrodes tend to land near 1.5 meters, well inside that envelope. From there, the drawing takes over. Outer profile and wall thickness, the inner bore, sharp or radiused corners, slots and through holes for the conductor and mounting, ground or chamfered end faces, and purity grade from 95 up to 99.7%. On the longer tubes, straightness is checked rather than assumed. Step back to where these tubes earn their keep, the corona treatment of plastic film. In that role, the ceramic profile delivers, point by point. It holds kilovolt insulation. It survives continuous ozone. It seats precisely in the cassette. It resists edge chipping. And it is replaced one tube at a time. Polyethylene, polypropylene, and PET arrive with surfaces to slick to bond. Ink, adhesive, and coating bead up and slide off. Driving the web under a high-voltage corona raises that surface energy so print and lamination take hold. The electrode that delivers the discharge is built from square ceramic tubes carrying a metal conductor down the center, clamped in a removable cassette above a rotating roller. Each tube insulates that conductor, shapes the discharge along its length, and absorbs the heat and ozone of nonstop production. Because the array is modular, a single cracked or worn tube can be swapped without rebuilding the whole electrode. Which is why matched dimensions and repeatable edges matter as much as the raw material.